Okay, Unit 4, Exponential Functions and Financial Applications. So Lesson 1 looks at exponential growth and decay. So the first half of the unit we're going to be looking at exponential growth and decay, and then the second half of the unit we're going to look at financial applications. So for the first lesson we have exponential growth and decay. So here's a problem where we can see some exponential growth and decay. Last year, many students ate inside the classroom, which led to an outbreak of fruit flies. The population of fruit flies tripled every day. If the initial population was 5 fruit flies, determine the population of fruit flies after 2 days and then after 1 week. So I'm going to draw a little table here just to try to organize my work. And I'm going to look at the number of days versus the number of fruit flies. And I'm going to try to figure out how many fruit flies there were at the end of 2 days. So initially, on day 0, there were 5 fruit flies. And after 1 day, and we're going to figure this out for 2 days, after 1 day, because we know that the population of fruit flies tripled every day, we know that after 1 day there's going to be 3 times the amount that there was previously, so that would make it 15. And then after 2 days, there would be 3 times that amount, which would make it 45. Okay, so each day the population tripled. Okay, in part B we want to know what the population is after 1 week. So that means that's 7 days. So 3, 4, 5, 6, 7. So I'm going to continue the table there. And what I need to do is triple each of these amounts, because on day 3 there's going to be triple the amount that there was on day 2. So 45 times 3 gives me 135. And I'm going to keep continuing this pattern until I figure out how many fruit flies there are after 1 week. So I get 1215 on the 5th day. You can see how nasty this is starting to get. These are fruit flies. Think about how gross it is to have that many fruit flies around you. And after a week, there are 10,935 fruit flies. Luckily though, fruit flies don't have a very long lifespan, so there wasn't actually that many fruit flies after a week. Okay, there's got to be an easier way to figure out this number, especially if I ask you how many fruit flies there would be after 2 weeks, because the last thing you want to do is sit here and continue this table. And so if we think about what information we know, well, you can notice that each time we're multiplying by 3. So this is actually a common multiple for each of these values. And so a formula that I can use for the number of fruit flies is the number of fruit flies over time is equal to the 5 fruit flies that we had initially multiplied by how quickly they are increasing. So they're increasing by a multiple of 3 with an exponent of t. So this is actually the formula we can use to figure out the number of fruit flies. Now if I wanted to know the number of fruit flies after a week, all I need to do is plug it into the formula. And I get 5 times 3 to the exponent 7. And if I do this on the calculator, 5 times 3 to the exponent 7 is equal to 10,935 fruit flies. And if you actually look at our table, we get the exact same answer. So we're going to look at how to write our a formula here so that we can figure out the number of fruit flies or any other insect or object when we look at an exponential growth or decay. Okay, so let's look at the definition of exponential growth and decay. So exponential growth and decay occurs when quantities increase or decrease at a rate proportional to the quantity present. So for example, increase or decrease by a constant multiple, either tripling, doubling, looking at half the amount each time, or looking at a certain percentage increase or decrease. Those are the kinds of things where you would look at exponential growth and decay. Oftentimes it occurs in science, so looking at populations, radioactive chemicals, as well as business when you're looking at finance and some accounts. Okay, so in terms of exponential growth functions have the following properties. First of all, if you look at the graph, you'll notice that the graph is increasing from left to right, so that's an exponential growth. So what happens is, as the independent variable increases by a constant amount, so for example, as the independent variable increases by 1s or 2s, the dependent variable increases by a common factor or constant multiple. So the dependent variable would increase by a multiple of 2 or a multiple of 3 each time. The graph, if you notice it, is increasing at an increasing rate. So initially it increases slowly, but as you move across it starts to increase a lot faster. And what you'll notice is that the growth ratio, which is the value of the base of the function, so whatever the exponent is raised to, that base value is greater than 1 when you're looking at an exponential growth. So the growth ratio is a value greater than 1. Similarly, when you're looking at exponential decay functions have the following properties. As the independent variable increases by a constant amount, so as you move across by 1s or 2s or whatever you want, the dependent variable decreases by a common factor. So what ends up happening is it's decreasing by a common factor, so decreasing by a half or decreasing by a third each time. Okay, so the graph decreases at a decreasing rate. So initially it's decreasing really fast, and then it starts to decrease a lot slower and slower as you move across the graph. Okay, so there's a huge jump, and then the jumps get smaller and smaller as you move across. And the decay ratio is a value between 0 and 1. So the base of the function is a number that's between 0 and 1. So for example, this could be y equals 1/2 to the exponent x, whereas the previous example could be something like y equals 2 to the exponent x. Okay. So before we move on, just to summarize what the equation that represents exponential growth or decay looks like. So the equation that represents exponential growth or decay is y equals a times b to the exponent x, where a is the initial value, so that's the initial amount of the object that you're looking at. B is either the growth or decay ratio, so it tells you the multiple that you're increasing or decreasing by. So a multiple of 2, multiple of a half, whatever the value is. And x is a number of growth or decay periods. So this tells you the number of times that the population or the bacteria or whatever you are looking at increases or decreases. So it tells you the number of times it's happening. Okay, so for exponential growth, the growth ratio, b, is greater than 1. So you're going to have a value that's greater than 1. It's also going to be equal to 1 plus the growth rate. Sometimes when you're looking at a percentage increase or decrease, you're looking at a growth rate, so increasing by 5% or decreasing by 10%. Those are examples of rates, and so you do need to figure out the growth ratio based on whatever the growth rate is. So for example, here's an example of an exponential growth. Here's the growth ratio. And the amount higher than 1 tells you what the growth rate is as a percentage. So this is 0.05 higher than 1, so that tells me that the growth rate is 5%. Similarly, when you're looking at exponential decay, the decay ratio is actually less than 1, so it's actually between 0 and 1. And it's equal to 1 minus the decay rate. So here's an example here. Y equals 45,000 times 0.9 to the exponent x. First of all, the fact that this value here is less than 1, so it's between 0 and 1, tells me that this is an exponential decay because it's getting smaller and smaller as you move across the graph. And this value here represents the decay ratio. So I'll just write down decay ratio. And I know it's decaying because it's less than 1. And the way you would figure out the decay rate as a result of the ratio is to look at how much less than 1 this actually is. So this is 0.1 less than 1, and 0.1 as a decimal is 10%. So that's how I know the decay rate is 10%. Okay? So the growth and decay rate is equal to the percent increase or decrease from one point to the next. So we're going to look at a couple of examples. Here's our first one. In a bacteria culture, the number of bacteria doubles each day. So that's some information about what the ratio might be. And the initial population is 22 bacteria. So it tells you how many bacteria you have initially. In part A, it asks us to determine an equation to represent the number of bacteria in the population after t days. So I'm going to start by writing the general form of exponential growth or decay. And I know in this case this is going to be a growth because it's doubling each day, so it's going to get higher and higher each day. And so if I plug in the information I know, the initial population was 22. So I know A is going to be 22. And because I'm looking at a population, I'm going to write this as P of T equals, okay, so the population over time in days, I already know the time is in days, is equal to 22 bacteria, because that's how much I have initially, times whatever the amount is that I'm going to be multiplying by each time. And in this case, because it's doubling, I'm going to be multiplying by 2 each time, to the exponent T, depending on the number of days that the bacteria is growing. And then it says use the equation to determine the number of bacteria in the culture after 1 week. Now you want to be careful. It's very tempting to plug in t equal to 1, but remember that t is in days, so we need to make sure that our time value is also in days. So 1 week is equivalent to 7 days, so we want to make sure we're looking at 7 days. So all I'm going to do is I'm going to take the function that I created earlier, and I'm going to replace t with 7, so find p of 7. And I'll use my calculator to evaluate that since I know all the information. So I have 22 times 2 to the exponent 7. And please be careful, you can't multiply the 22 and the 2 yet. The 2 has an exponent of 7, so please make sure you evaluate the exponential part and then multiply it by 22 afterwards. And you get p of 7 is equal to 2,816. So there are about 2,816 bacteria after 1 week. So therefore, there are 2,816 bacteria in 1 week. Okay, let's look at our second example. This one's a little bit different. So in this example, you're not told what the ratio is. You will need to figure it out. And what it says is the effectiveness of deodorant decreases at a rate of 8.2% per hour with normal physical activities as the day progresses. First of all, the fact that the question tells me it's decreasing tells me that I'm going to have a decay ratio. So the value that I'm multiplying by, such as here, is actually going to be less than 1 instead of greater than 1. Okay? So in part A, it says determine an equation to represent the effectiveness of the deodorant after t hours. So again, because I know this is an exponential growth or decay, I'm going to start with the formula. And then I'm going to plug in the information that I know. So my t value is already in hours, that I already know. What I need to figure out is what variable I should use for y. So because I'm looking at the effectiveness of deodorant, I'll start by using E of t. So the effectiveness over time is equal to. Now your initial amount is not given in this case, but because you're looking at deodorant, normally as soon as you put deodorant on, it's 100% effective. So that tells me my A value is equal to 100%. It has to be 100% effective when you just put it on. Okay? And now our decay ratio, since I know it's decreasing over time, is what I need to solve for. Because it's the decay rate is 8.2%, what I'm going to do is start with a decay ratio of 1, and I'm going to decrease it by 8.2% since it's decaying or decreasing in effectiveness over time. And so if I do that, I get a decay ratio of, so 1 minus 0.082 gives me 0.918. And if I plug in these numbers, I can come up with the equation to represent the effectiveness of the deodorant. So I get 100 times 0.918 to the exponent t. Okay, so the effectiveness starts off at 100% and then decreases by 0.918. That's our decay ratio, depending on how many hours we're looking at. And then it says Jason puts on his deodorant. I guess that's Jason in the picture there. At 8:30 a.m. just before he leaves to go to work. Use the equation to determine how effective his deodorant is at 3:30 p.m. when he arrives home. So first we need to figure out how much time that is. Because our time is in hours in our equation, we need to figure out how many hours this has been. And so from 8:30 to 3:30, that's 7 hours. So that now we know that t is equal to 7 hours. And so all we need to do is use our equation and substitute in the information that we know. And so I have E of 7 is equal to 100 times 0.918 to the exponent 7. And I can figure out what that amount is by using my calculator. So 100 times 0.918 to the exponent 7. And that gives me about 55%. Okay, so when he gets home, the deodorant is only about half as effective as it was when he put it on. Okay, so therefore, the deodorant is about 55% effective. What does that mean? He needs to put it on again. And that's it.